In this video, we'll be looking at benzene in terms of hybridization and resonance. Benzene has a molecular formula, which is C6H6, where the 6 carbon atoms are bonded to each other in a ring, right, a 6 carbon ring, and each carbon atom is bonded to a hydrogen atom. Initially, benzene's benzene's structure, which was derived by Kekulé, in his determination of the structure, he proposed that it could have existed as two possible structures or isomers. If we look to the center of the diagram, we're going to see Kekulé's structure, which shows alternating single and double bonds. The two structures are considered to be distinct or isomers of each other. If we look to carbon atom 1 and 2, which I have just labeled, so I'm looking at carbon atom 1 and 2 on the first isomer versus carbon atom 1 and 2 on the second isomer. In the first isomer, we see a double bond. In the second one, we see a single bond. So in Kekulé's proposed structures, he considered it to be made up of alternating single and double bonds. If that were true, in measuring the bond length within this benzene structure, two bond lengths consistent with a single and a double bond would have been obtained. However, as seen in the third diagram, the actual bond length present between the carbon atoms in the structure of benzene was the same, indicating that there are no alternating single and double bonds. It, however, does show that the bond angle is 120 degrees and that the carbon atoms are arranged in a hexagonal planar ring. How do we explain identical bond lengths and a bond angle of 120 degrees, which indicates that each carbon atom has surrounding it 3 bond pairs? If we look to the diagram below, where we see sigma bonds, sp2 hybridized orbitals, this will explain our planar hexagonal ring. In each carbon atom, a 1s orbital and 2p orbitals mix to give us 3 sp2 hybrid orbitals per carbon atom. These 3 sp2 hybrid orbitals give rise to the carbon to hydrogen bond for each carbon atom, as well as each carbon is bonded to 2 other carbon atoms. So our 3 sp2 hybrid orbitals will end-on overlap with 2 other carbon atoms and 1 hydrogen atom to give us 3 sigma bonds in total. So each carbon bonds via 3 sigma bonds. So for each carbon, if 1s orbital and 2p orbitals are used to form hybrid orbitals, that means for each carbon atom, there exists 1 pure p atomic orbital. This pure p atomic orbital exists above and below our hexagonal planar ring of carbon atoms, which is bonded via sp2 hybrid orbitals. Because of how adjacent the pure p atomic orbitals are to each other within this hexagonal ring, the p orbitals will overlap sideways above and below our hexagonal planar ring, to give us what is called a delocalized pi electron ring system. That is, a region of high electron density above and below our plane of carbon atoms. This is what we consider to be our structure of benzene. And this structure is what we call a resonance structure. Our resonance structure we draw very simply as our hexagonal ring with a circle in the middle. I will summarize by looking at this short note. Let's look at what this term resonance means. Benzene is a molecule that exhibits resonance. Resonance means that its structure can be represented by a composite structure. So I'm going to draw Kekule's two structures. So with Kekule's structure, where it was thought to consist of alternating double bonds, with a resonance hybrid, the resonance hybrid structure is said to be a composite made up of these two proposed structures of alternating single and double bonds, where in our resonance hybrid, we consider our structure benzene to consist of a delocalized pi electron ring system, which we represent as a circle at the center of benzene. And this delocalized pi electron ring system exists above and below our hexagonal ring of carbon atoms, and it is meant to be a composite structure which shows an arrangement which represents this arrangement of alternating single and double bonds as a quote-unquote composite structure. And this is what a resonance hybrid is. It does take into account the two possible structures as a composite structure. Right, so without talking about it too much, that's our resonance hybrid. And just to wrap up, we'll look at the structure of benzene in a short note by saying that benzene consists of 6 carbon atoms arranged in a hexagonal planar ring. And we count our carbon atoms from the top: 1, 2, 3, 4, 5, 6. It's considered to be a planar ring of carbon atoms, a hexagonal ring with 6 carbon atoms, where a delocalized pi electron ring system is said to be formed above and below this plane, and this delocalized pi electron density is a region of high electron density. Why is it considered a region of high electron density? This is because on each carbon atom we have a pure p atomic orbital, and these p orbitals overlap sideways, and on overlapping sideways, that gives us our pi electron ring system. Within our hexagonal ring of carbon atoms, each carbon is bonded to 2 other carbon atoms. So we have 1 sigma bond and another. So this is for each carbon atom. And each carbon is also bonded to a hydrogen atom. So this is also a sigma bond. So this gives us 3 sigma bonds in total. And also summarizes that our three sp2 hybrid orbitals are all engaged in some form of bonding. And that leaves us with our pure p orbital, which exists above and below the plane of our sigma bonds, and their overlap gives us this pi electron ring system. Because of our three sigma bonds in this hexagonal planar ring, this gives us a bond angle of 120, right, for each carbon atom. And this is my short video on resonance and benzene.